It's my pleasure to introduce our speaker today. There's a couple of things that make you feel old. One of them is when you have students that have then gone on to get a PhD and then come back to teach at Wittenberg, and then you realize I've been teaching at Wittenberg for 4 years. That's starting to get there. And so I knew her as Alyssa Armstrong. You may know her as Alyssa Hoofnagle. Please welcome Alyssa, who will be talking about how to count without actually counting.
Okay, well, thank you all for being here. I think this is one of the busier packed houses. So hopefully I don't bore you all to death about combinatorics. But I want to first talk about what the heck combinatorics is. And so I started Googling definitions of combinatorics. And so the Oxford English Dictionary, which is kind of the end-all be-all of dictionaries, described combinatorics as a branch of math that, and so kind of look for these highlighted words that I picked out. So the OED says it studies the possible combinations of configurations. Collins Dictionary, which is a little more involved, said it's concerned with the theory of enumeration, which again is kind of, we can justify as being mostly about combinations and permutations, which we'll talk about later. In order to solve problems about the possibility of constructing arrangements of objects that satisfy some specified conditions. Wikipedia says, in 5 words, studies finite or countable discrete structures. Again, the word countable, kind of counting in there, and there's a mathematical definition for countable, which I'm not going to get into. And also, discrete means whole objects or whole numbers. So we're not talking about fractions or decimals or anything like that when we're talking about these discrete structures. The Encyclopedia Britannica, this is the last one I promise, says it's concerned with the problems of selection, arrangement, and operation within a finite or discrete system. So again, that word discrete pops up. And then it keeps on going to say one of the basic problems is to determine the number of possible configurations of a given type. And so if you think about or kind of look at those sort of orange highlighted words, we have a lot of things about combinations or kind of counting in there, configurations or arrangements, and then various verbs associated with them. So I kind of summarize these all together as selecting, arranging, constructing, classifying, and then kind of what we'll talk about counting or listing objects is kind of the main idea of what combinatorics is about. And so that's kind of where we'll move. We'll talk about different, kind of in a historical context especially, different ways people have counted or arranged or constructed or selected objects in this way. Okay? So this history and the history of combinatorics, I think all math history is really interesting, but the field of combinatorics, I think, became really well known more recently, but it actually has ties back to ancient times. And so I want to go back to kind of as civilization was taking shape. And so one of the first kind of places this comes up, or what we'll talk about today comes up, is back in ancient China. And so the I Ching, which is the Book of Change, translated Book of Change, is one of these 5 classic books that is used in Confucian wisdom. And so there are 64 chapters in this book, and each chapter sort of symbolized or headed with a hexagram, which consists of 6 lines, and they go from bottom to top, so line 1 is actually on the bottom. And these lines are either dashed or solid. And the dashed lines are what they call the yin, and the solid lines are the yang. And so if you've heard yin and yang before, that's where this was used as well. And so this is an example of hexagram. Again, bottom to top, it's got 3 yins, 3 dashed lines, and then 3 yang, 3 solid lines on top of it. And so problem that people were interested in with this was how to arrange all these different hexagrams with these chapters. And so you'll notice that there are 6 lines, and each line you have 2 choices. It could be either solid or dashed, and so you have 2 choices for each of those 6 lines, which gives you 2 to the 6 or 64 chapters. And so each one of the chapters in this book has this hexagram, and so there were different ways of arranging these 64 symbols. And so back in 1100 BC, okay, we're talking BC, way back, King Wen arranged them in pairs. And so you kind of notice this was his arrangement. And so they're sort of complementary. If you look at kind of the top first two, and I know the symbols are kind of small, but the first two have all yangs, all solid lines, and then the next one is all yins, all dashed lines. And so you'll kind of notice, if you look at the pair that are labeled 3, 4, it has a yang at the bottom, and then 3 yins, a yang and a yin, and then it sort of flips that symbol upside down to get 4, kind of the opposite with that. So he kind of arranged these in a complementary style. There are a few symbols that are symmetric when you flip them upside down, and so he just kind of threw them in the middle there. But he arranged them back in 1100 BC in this way. And then it wasn't until, well, people continued to look at this, but Shaoyang introduced another arrangement in 1060 AD, so quite a bit of time later, that started with all yangs. So you'll notice we've got up in that top left corner all solid lines, and then introduced kind of one dashed line at a time, and started at the bottom and worked its way up. And so you'll notice we have kind of a dashed line in 2 at the bottom, and then that dashed line moves up to the second line in 3, to the third line in 4, and so on. And so he kind of introduces this more progressive way of arranging these symbols. And so again, these are all arrangements of these 65 or 64 symbols that we have done back, even 1060 AD was a long, long time ago. And so, so that was where, a little bit of kind of where things came up in China. In ancient India, others worked on arranging syllables in these sacred Vedic chains. And so syllables that were written in Sanskrit at the time were either short or long. And so you kind of have that 2 kind of solid versus dash line similarity here. And a typical verse, poetic verse that these people were looking at consisted of 4 lines with n syllables each. And so the prosodists who were studying these wanted to classify all 2 to the n possibilities. Again, you've got 2 choices for each syllable, you've got n syllables, and so we've got 2 to the n possible choices for these syllables. And so in 400 AD, Pingala described procedures that where you could find out of his arrangement whatever kind of syllable pattern, whatever syllable pattern that was K, kind of K in the list, where that was, as well as how to find that pattern. So we had this very formulaic process of describing the syllables and as they changed kind of from probably all short to all long, or vice versa. Also, in the 8th century, okay, so a little later, Kadara gave a step-by-step procedure for listing all of these. So Pingala kind of gave you the general pattern, and Kadara actually gave this process of listing all of the arrangements. And so these ideas, done back in ancient China and ancient India, were eventually connected to the binary number system. If we've got computer scientists or anyone who's studying computer science in the room, binary deals with 2 choices, right, 0s and 1s. So it connects to the binary number system. It also connects to Pascal's triangle, which I'll talk a little bit more later. Kind of, if you've seen Pascal's triangle, it deals with these ideas. It connects to the Fibonacci sequence, so these syllable patterns relate to the Fibonacci numbers in some way. And also Morse code, which you can kind of think of those solid and dashed lines as being Morse code as well. So a lot of times these get called Morse code problems because they're looking at 2 options, kind of solid versus dashed. And so early history has led to these, hopefully you've heard of some of these famous kind of ideas in there as well. But the work that was done led to this formal description of what we call a permutation. And so, and we'll start with permutations and then kind of lead into combinations from there. So our definition, this is a very intuitive definition, but I think it helps you kind of see what's going on. A permutation on a set of objects, we're going to call that set S, is some ordered arrangement. So the key word is that it's ordered arrangement of the elements of S. And so as an example, if S consists of the set 1, 2, 3, 4, and 5, Then we have two permutations up here, and they're written kind of differently, so I'll kind of explain what this means. But we're essentially taking the numbers 1 through 5 and reordering them in some way. Okay, and so sigma here, the way this works is we kind of list the original elements in the order that they were given in S, and again, S, the order doesn't matter too much, but we like to kind of keep track of where, kind of what the first position is, what the second position is, and so on, because we're ordering these. And so sigma would say we're going to choose element 3 to be first, and then element 1 to be second, element 4 to be third, and so on. Okay, so we have sigma as a permutation that kind of mixes up all of the numbers. And then mu is also a permutation, but you'll notice we chose kind of 1, 2, and 4 to all be in their normal positions. 1 is first, 2 is second, 4 is fourth, and we just kind of switch 3 and 5 around. And that's a valid permutation as well. We can always keep elements kind of where they should be, especially when we're talking about numbers. Okay, but the key is that they're ordered, that if I rearrange the numbers in a different way, I would get a different permutation. Okay, and it can be shown, and this is a kind of classic first step when you're thinking about permutations, that if your set has n things in it, then there are n factorial permutations. And so a quick explanation here is that if we have n elements, so you can kind of think of this in our example with 5 elements, we have 5 choices for what we want that first element in the list to be, and then we've used it, and so we only have 4 left. And so then we've got 4 choices for what we want the second element in our list to be, and so on. Then we've used that, and we only have 3 left, and so on. And there's a principle in counting that I didn't put up, but using the first element in the list and then the second element and so on, we can multiply those choices together. And so this is where the formula n factorial comes from. You start with n, multiply by every consecutive lower integer until you get down to 1. Okay? And so you'll notice that even if n is small, 5 factorial, for instance, is fairly large. And so these ideas of permutations get very large very quickly. And so kind of back to some history. So non-trivial lists of these permutations, like I said, they're large sets of things, were not published until hundreds of years after we discovered that n factorial formula. And so actually getting these lists took a lot more time than knowing or being able to think about n factorial and why that makes sense for the number of permutations. And so in 1884, an Italian physicist listed all the permutations of length 5. Okay, so all 120, which is 5 factorial. And he actually did this using Hebrew letters, so it's really interesting. It's not using our traditional Latin letter system. And then he went on to list 120 permutations, but with 6 letters, where he fixed that first letter. So you can kind of think he did this in Hebrew again, but if you think about letter A as being that first letter always, the remaining 5 letters, he could work on the permutations in the exact same way he did before. And then he noted that if you changed, instead of starting with letter A, you started with letter B and did the same thing with the 5 letters that were left, and then letter C and so on, you got 6 sets of 120 permutations, and that led to the 720 permutation number that he needed. However, his list was super haphazardly fashioned. He did this kind of in not a very formulaic manner, and so he missed some out of the 720. And so it led to errors, but he knew that he should have 720 permutations on 6 elements in a set. And then actually, earlier, back in 1629, Jeremias Drexel actually gave a complete list of 720 permutations with 6 elements. And he offered the list, and I think this is kind of fun, he offered the list as a proof that he could have a man or somebody else could have 6 guests over for lunch and dinner every day for a year, and could seat them in different spots at the table. Okay, so it's a really interesting proof, and you may be wondering, but we have 365 days in a year, and there are only 720 permutations, and he took out the fasting that was done at that time for Holy Week, leading up to Easter. So there was 5 days of fasting, And so lunch and dinner didn't happen during those 5 days. And then you get 360 remaining days in the year, multiply by 2 for lunch and dinner, and you get different guest seating arrangements every single day for a year. So permutation is very interesting. However, permutations talk about order. We really focus on the order of sets. And so we want to often think about sets, ways we can come up with unordered lists. So we don't care which is the first, which is the second, and so on. And so this is where it leads us into what we call combinations. Okay, and so there's slightly different notation here. A K combination, still on a set of objects, S, is an unordered arrangement. So the key word here is that it's unordered, and it's, again, kind of arrangement maybe a little loose here. It's an unordered way of selecting K elements from your set S. And the reason why we select smaller, usually K is smaller than our total number of elements in S, is if I had all elements in S, and I'm selecting all of them, and I don't care about the order, I get S back itself. I don't, the order removes the need to think about all elements in S. And so an example here, again, S is going to be our set 1 through 5, just like normal. And say we're looking at the combinations with 3 elements in them. So we want to not look at all 5 elements, but we want to select 3 of them. Order doesn't matter. And so selecting, say this first set, 1, 2, 3, is the exact same if I selected 1 first, then 2 second, and then 3 third. It's the same as if I had selected 2 first, and then 3 second, and 1 third. And so the order doesn't matter. So we specify these instead of a list, kind of like the last notation with permutations, we specify them as sets themselves. Okay, so we have 10 different ways of selecting 3 things that are unordered from 5, and they're listed here. Okay? And so the next kind of major idea is, well, you kind of notice for 5, a set with 5 elements, and we're selecting 3 of the 5, well, how many are we guaranteed? How many ways of doing this are we guaranteed? And this is another good problem, but it can be shown that if you have n elements in your set, and you're selecting k of them, then we end up with the total number of ways to do this is this binomial coefficient. It's read n choose k in the way that we think of choosing elements from sets, and it's based on factorials. So the number of combinations where you're selecting k elements from a set with n is given here. And we read these as n choose k. And these are going to come back, so just kind of keep that in mind as we go. Okay. Combinations also have a really rich history. The earliest exhaustive list of combinations appears in this, not a math paper, but appears in this treatise on medicine. So this came up when thinking about medicines, and this Susruta wrote this treatise that was written at least by 600 AD. They think it could have come out beforehand, they just can't date it as well. And so he noted that medicine could have one of 6 kind of qualities. So it could be sweet, sour, salty, pungent, bitter, or astringent. And so then he was thinking about, for a particular medicine that could have multiple qualities attached to it, how many different ways could you come up with these combinations? And so he found that, if you were just looking at one type of medicine only, you had 6 possible ways of selecting one of those 6 choices. You have 15 ways of selecting 2 of them. 20 ways for selecting 3, so picking 3 from that list of 6. 15 of selecting 4, 6 of selecting all 5, which is kind of the same as kind of discluding 1. So that's how we get the same as 6, the 6 in the first type. And then 1 combination to select all 6. Right? There's 1 way to get all 6 of those qualities. And this is actually what leads us to what we call the Pascal's triangle. These are the coefficients that come up in that triangle, and they're all based on combinations. And so if you're interested, you can look up Pascal's triangle and see what's going on there. And so again, these ideas of combinations did not show up in math. kind of journals or publications or even letters between mathematicians until well after a lot of other non-mathematicians started to think about these things. And so it's really, really interesting to see how, especially in the field of combinatorics, how these ideas that we formalize mathematically came up years and hundreds of years before they were formalized. And so in Europe, this also, people were also still thinking about combinations. And one of my favorite stories, and often what comes out of these ideas involving permutations and combinations and just counting in general, deals with gambling and recreational games. And so back in Europe in medieval times, they were often interested in dice throwing. And so the idea was 3 dice were thrown, and they wanted to see how many different ways you could get 3 2s or 2 2s and a 4, that sort of thing, in the kind of gambling sense. And so back in 985, a Bishop Wiebold, who was in northern France, wanted to play dice rolling and gamble, but as a clergy member, it was frowned upon as being not very pious, and so he developed this new game. So you could still roll 3 dice, and he attributed every single possibility of those 3 dice rolls. And again, these dice are not differentiated in any way, and so they're all kind of standard dice. You don't know which one you threw first. You just kind of grabbed 3 dice and rolled it. And so each one of the options that you could get, so say you got 3 1s, he attributed to a certain virtue. And so the clergymen could roll the dice, and that was the virtue they were going to strive for, throughout their time. And so, but kind of thinking about this, he had to come up with how many different virtues he needed to fit with these dice. And he found that there were 56 ways to roll 3 dice. And this is slightly a little more complicated because, again, rolling 3 dice, you could have repetition. You could end up with 2 2s. When you roll the dice. And so there are kind of 3 ways to think about this. So there's a possibility to roll all 3 of the same number. And so there are 6 ways to do that, right?